subscribe, do it, please. Yes. Last week, I said I was going to talk about Assosiohedra, but specifically, what are Assosiohedra? Before we talk about Assosiohedra, we have to talk about associativity. Associativity states that A times B equals B times A. Now that might seem so obvious that it doesn't need a name, but a lot of things don't have associativity, just like the thing I was going to talk about today. And, well, associativity, we have to talk about loops. What is a loop? What classifies as a loop? This is not a loop. This is not a loop. Not loops. Things like this, none of those are loops. But these are loops. That's a cue. These are loops. Things like this, those are all loops. So let's delete all of this. So what if you put two loops together like this, and they all have the same endpoint? Let's call this one A and this one B. You can think of it at a loop as a car driving around it, and a loop A times a loop B. You could draw 0 to 1. Oh, 1 second. Yeah, 0 to 1. And A goes along this one, and B goes along this one. A times B is this. And if we draw another line, then we put B times A. We have B and then A. And we classify these as not the same. So we can say that A times B equals -1 times B times A. Makes sense, right? So we can say this is A times B, this is B times A, and that line, if you were to smoothly transform this one into this one, that is called a homotopy. That's called a homotopy. Homotopies are very important in law of subjects, but for now, this line is a homotopy between A times B and B times A. So that means a association for this loop is a line, and a line is to these loops, or the figure eight. Okay, if that doesn't make sense, then go watch Infinite Series video. I will link it in the description. It is super helpful to understanding math in general. So yes, we have this. What if you do 3 loops? 1, 2, 3. I'm going to do a few examples of this so you can get a hang of it. A, B, C. We can put A, B, C like this. We can put A, B, C like this, which is pretty much the same thing. So I can get rid of that. We can have A, B, C. We can do A times B and then multiply that by C. And you can think of it as, so we start on the outside and we split the timeline from 0 seconds to 1 second and a half. So the front half would be C, and we split the first half in half, and we have A and B. So it goes A 1/4 of a second, B 1/4 of a second, C half a second. That should make sense. So you can have things, you can have a lot of things, and you can have two things, yeah, 2 things, just the same as the, and also, by the way, I mentioned I was wrong about the line thing for the 2. That's actually a point. If I ever make another mistake, please, if I don't call myself out, call me out on any mistakes I make. If you spot any mistakes, please call me out because I need to be called out for that. So yeah, these are the 2 ways, and you can draw a line for those, for the homotopy. So we can have 1, 2, 3, 4. Whoops, I am bad at drawing these, so please, drawing with a mouse is difficult. I'm going to label these A, B, C, D. Well, I'm not going to display all of them because that would take too much time. Well, actually, I can't display all of them. We can have A, B, C, D. First, we can put the brackets like this, this, you could do the mirror image of that, which would be A, B, C, D. I have enough time to display all of these. We have A, B, and C. We have that. On. Oh. We have that. We could have actually 5 of them. And what does a 5-sided polygon look like? You guessed it. It is literally a pentagon. 1, 2, 3, 4. Any pentagon will do. So we have a homotopy. Each side is a homotopy. But I did not mean to do that. But this whole thing is actually one homotopy. I'm not talking about the boundary. I'm about this whole pentagon. Because don't just go from here to here to here to here. You can go like this. You can go like this. You can go like, you just can't go outside of the pentagon. So that is 4. What about, I'm just gonna write it. What about A, B, C, D, E? Well, I can't really actually draw it, not because it's way too complicated, but it's a polyhedron with 9 faces, 2 squares, which I'm going to notate by F1, and 7 pentagons, which I'm going to label F2. So, what about all of these loops? Well, it turns out if you have F amount of loops, the Assosiohedron is F minus 2 dimensional. I should probably there. So, what about all the loops? It's called A infinity space. A infinity space. The A is for Assosiohedron because we have to remember this is Assosiohedra. And then infinity is for the eventual infinite amount of loops you can have. That is what Assosiohedra are. So that is the video. I think I'm going to start doing something called the fun factor. At the end of every video, I just state a fun fact relevant to the next video. If you guys don't like it, let me know in the comments, but if you do, also let me know. The fun fact for this one is that every rational number has a according not to it. That is a fun fact, and I will talk about rational knots and tangles next video. Bye. And remember to subscribe. It is easy and free. It is the red button. Should be somewhere down here. Somewhere below. Make sure to subscribe because, alright, yes. Bye.